seminar. So today it's my pleasure to introduce Olena Karpel from AGH Kraków, who will talk about dynamics and invariant measures for horizontally, especially generalized Bratteli diagrams.
Thank you very much. It's wonderful to be here again. Thank you, Artem, for the invitation. The talk will be mostly based on the preprint joined with Bezuglyi, Jorgensen, and Kwiatkowski. So we will be talking about generalized Bratteli diagrams. These are the graphs which are very useful in dynamical systems. They model homeomorphisms of Cantor spaces and also Borel automorphisms of standard Borel spaces. And these models are very useful to study, for instance, the simplex of invariant measures, to study some properties of the transformations, to see the number of minimal components. They are used to classify dynamical systems, and also they are very good for construction of various examples of transformations with given properties, like with the given number of ergodic and variant probability measures. So let me recall the definition. And I will define at once generalized Bratteli diagrams, but also maybe mention what are usual classical Bratteli diagrams. So a generalized Bratteli diagram so let me abbreviate by GPT. It's an infinite graph. So we have the set of vertices and edges. The set of vertices is partitioned into so-called levels, into disjoint subsets. For generalized diagrams, each of the subsets Vi is countably infinite. And so Vi is usually called the ith level of the diagram. So we have here V0, V1, and so on. And then the set of edges is also partitioned into disjoint subsets. And for every I, the edges from the set EI are drawn between vertices from VI and VI plus 1. So we assume that all edges are directed downwards. So all edges are directed downwards. So we have the source, each edge has the source and the range. So for every I, let us denote by n0 the set of natural numbers together with 0. So for every such level psi, for every E in EI, the range of E belongs to VI plus 1 and the source of E belongs to VI. So we draw edges like this. There can be multiple edges between vertices and so on. So another rule is as follows. For every vertex, there is an outgoing edge. There exists E such that the source of E is V, and for every vertex except for vertices of 0 level, there is an incoming edge. So for every V in V except for V0, there exists an edge which ends in this vertex. And the last rule, for every vertex, there are only finitely many incoming edges. So for every V in V is not V0, let's say R inverse of 4 of V, R inverse of A is finite.
But outcoming can be infinite.
Yes, can be infinite. So actually this will be the difference between a locally compact case and non-locally compact case. Exactly, so going can be infinitely many, and for standard Bratteli diagrams which are used in Cantor dynamics, we have only finitely many vertices on each level. And for generalized, we have now infinitely countably. And our space for the dynamical system is the path space of this graph. So we will denote it by xb. It's the set of all infinite paths which start from zero level and go downwards. So we have sequence of edges which form a path. And now we introduce topology of this path space, which is generated by finite paths or cylinder sets. And also we are interested in the case when xb is uncountable. So topology is generated by finite paths or cylinder sets. So once we have a finite path, we can consider, we will denote in square brackets the cylinder set. It's the subset of xb, which consists of all paths which initially pass through this finite path. So for every I from 0 to n, xi is equal to ei. And they form the base for topology. And with this topology, xb becomes a polar space. It's a complete separable metric space. In case when we have finitely many vertices on each level, and if we don't allow isolated points, we get a Cantor set. So this was this part. And now let us introduce, so as already it was asked, if we have finitely many outgoing edges from every vertex, we have a locally complex. But we don't require this, so we can have infinitely many outgoing edges from vertices. And now let me recall the dynamics, which was introduced by Bratteli-Vershik on this graph. So we have to define an ordered Bratteli diagram. Ordered generalized Bratteli diagram is done in the same way as for standard Bratteli diagrams. So we know that each vertex has only finitely many incoming edges, and we put a linear order on the set of those edges for each vertex. So two edges are comparable only if they have the same range. So let's say two edges E and E prime are comparable. So for instance here we order these edges, this and so on. We do it for every vertex. And then we can have so-called minimal and maximal paths. So it can be infinite, minimal and maximal paths can be defined both for infinite and for finite paths. So for instance, for infinite ones, the path is minimal if and only if for every I, the edge xi is minimal among all edges comparable to it. So among all edges that enter the same vertex, so it's just labeled by 0. And the same for maximal. And now just finitely many vertices on each level, then this set of infinite maximal paths and set of infinite minimal paths, they're always non-empty. It follows from compactness. But here we don't have compactness, so there are examples when these sets are empty. But so let's denote by x capital max the set of all infinite maximal paths. It can be empty, but it's always closed set. And by x min, the set of all infinite minimal paths. And now we can define the Vershik map. So first let's define a map from the set of non-maximal paths onto the set of non-minimal paths. And let's define as follows. So once we have arbitrary non-minimal path, that means that we can find the first non-maximal edge. Then this edge has a successor. So if our x consisted of the following edges, let's say it's k, so it's k. We define the image under the Vershik map of x as follows. Let us so xk was the first non-maximal edge. Let's denote by xk bar its successor, the next one. So we know that xk and xk bar, they have the same range. So we can remain the tail unchanged. The rest of the path, and we will have well-defined piece of the path. And now the source, of course, might change. So we join this new vertex, the source of xk bar, to the level v0 using the unique minimal path. So of course every vertex is joined by the vertices of 0 level by unique minimal path, unique maximal path, and the number of finite paths that join a given vertex with v0 is finite. This y0, yk is the unique minimal path which joins the source of xk with v0. And now if it is possible to prolong this map to the whole path space xb, mapping all maximal paths onto all minimal paths in such a way that we get a Borel automorphism, then we have a generalized Borel-Vershik system. For standard Bratteli diagrams, we want to have a homomorphism. So if it is possible to prolong this Vershik map phi b to a Borel automorphism of xp, then we have a generalized Borel-Vershik system. So let's maybe recall some.
Can I have a question?
Yes.
So why is it obvious that if you take a non-maximal path and do this procedure, then you get a non-minimal path of the outcome?
Because this one is successor, right? So it's not a minimal edge.
Okay.
Right? Minimal path consists of all minimal edges, and in the image we have for sure non-minimal edge.
Right. Okay.
And actually, but thank you for the question, because one can check that phi b from the set of non-maximal paths onto the set of non-minimal is a homeomorphism.
Okay.
It's always so one can define in the same way the inverse procedure. We look at the first non-minimal edge, take its predecessor, and join the source by maximal path.
So in particular, it could map a non-maximal path to a maximal one,
Of
right?
course,
It's just
yes,
right and
absolutely.
left.
So let's consider an example which will be useful also later. In this example, we will consider just standard Bratteli diagram, but we will anyway need this notion of this diagram later. So it is so-called odometer. Let's consider a Bratteli diagram which has just single vertex on each level. Okay. So this is the case of standard Bratteli diagrams. And let's consider dyadic odometers. So we have just two edges between consecutive pairs of vertices. And we can put an equation, anything. And so let us look at the image. So there is unique minimal path and unique maximal path, right? And let us look at the image of the unique minimal path. So this is our first non-maximal edge. It's mapped to a successor and tail remains unchanged. So we get 1, 0, 0. Now if we look at the second image, let's see. So we have to apply Vershik map to this path. 1 is maximal, but then 0 is non-maximal. So it's mapped to maximal. We join this vertex to this 0 with the minimal path, and the tail remains unchanged. So we have 0, 1, 0, and so on. So you can see that we add +1 and have carry to the right. And so on. And here we can map unique maximal paths onto unique minimal path. And then we will get a homeomorphism. So in general, for standard Bratteli diagrams, if we have unique minimal, unique maximal path, then we can always map this maximal to minimal and get a homeomorphism. So this is called odometer. And now let me see. Okay, so maybe let me mention a couple of theorems. So maybe one of the most classical ones about standard diagrams and then about generalized. So it was proved by him, Hartman and Scow. In 1992 that any minimal homeomorphism of a Cantor space is topologically conjugate to a Vershik map acting on a path space of a Bratteli diagram. There are some more conditions. One can say even more precisely that this diagram can be built to have unique minimal, unique maximal path and be so-called simple. It will mean that roughly that on consecutive levels, all vertices are joined by edges. But this is for standard diagram. So let me write down that any minimal homeomorphism of a Cantor space is topologically conjugate to a Vershik map acting on a path space. Let me just write down this formulation of a simple. So this means that these neighboring vertices are connected by edges, all of them. Of a simple, properly ordered, it means unique minimal, unique maximal path. Of a simple, properly ordered standard Bratteli diagram. And maybe a couple of words why this is true. So let us look at our Bratteli diagram, for instance, at the vertices of level n. So there are finitely many paths which join each vertex from level n to the vertices of 0 level. And among this path there is unique minimal, unique maximal path, and all these paths can be compared with the So before we compare just single edges, now we can compare two finite paths that enter the same vertex. So if we have, for instance, one path and then another one, such that the ranges of these last edges are the same, we can just we can look at these last edges, En prime. If En is smaller than En prime, then this whole path is smaller than this one. If they are the same, that means that the previous edges, En minus 1, En minus 1 prime, have the same range and again can be compared. So we can compare any two such paths. And Vershik map will map, for instance, this minimal cylinder set to the next one, to the next one, to the next one, up to maximal, using this lexicographical order. So we see that for every W, if we just draw this set like rotated, we see that we have so-called tower, and the Vershik map, these are the levels of the tower, and Vershik map maps each level to the next one until we get to the maximum, and then in order to know how to map the points, we have to go one level down. So we have to do cutting and stacking procedure, which corresponds to the way the edges are drawn between levels and to the order. Maybe we'll also need this. So let's denote by x w n this tower which corresponds to the vertex w on level n. So in other words, it's the set of all infinite paths such that they pass through w. And then, so it's the union of these cylinder sets. So such that Rfxn minus 1 is w. And then there is a notion of a height of a tower. It's the number of levels. So the height is denoted by hwn. So this is tower. This is height. It's the number of finite paths that join w to this level. Number of finite paths that join w to V0. So we see that our ordered Bratteli-Vershik is actually a nested sequence of Kakutani-Rohlin partitions. Right? So Kakutani-Rohlin partition is exactly the partition of this form which has towers. And the Kakutani-Rohlin partition for a Cantor minimal system, it's a Klopen partition of the following form. We have Cj, Ck, where Ck are the bases of the towers. They correspond to these minimum cylinders. So Ck is Klopen. There are finitely many of them. Index J changes from 0 to the height of the corresponding tower case. Maybe I will write here. So Ck is Klopen, K belongs, it's for Cantor minimal systems, K belongs to some finite set of indices, and J changes from 0 to the height which corresponds to K. So exactly what we see on the Bratteli diagram on level n is partitioned into towers. And then when we go to the next level, we sub-partition here every cylinder set. So we do cutting according to how many outgoing edges we have. And then we rearrange these pieces. So we build now new towers which consist of pieces of previous towers. So Bratteli diagram is just a nested sequence of Kakutani-Rohlin partitions for the Vershik map.
The original Kakutani-Rohlin was for measured precisely.
Yeah, but then it was done for topological dynamics.
Why couldn't?
Here on bottom scale, I think. So Vershik did it in considered measurable partitions, but then Herman, Putnam, and Scow, they refined his construction for topological minimums. Yes, thank you for your remark. So, and how do we build from a Cantor minimal system, for instance, this diagram? So it's clear that if we have a Bratteli diagram which has unique minimal maximal path and such that on each sequence of on each pair of neighboring levels all vertices are connected with each other, we get a minimal homeomorphism. The Vershik map is minimal because all vertices are connected to the vertices of previous level, so the orbit of every point is dense. So we get a minimal homeomorphism, and vice versa. Once we have a Cantor space and a minimal homeomorphism, we can pick any point which will become later our unique minimal path. And for instance, if we take any open neighborhood at this point, we can consider return times of the point from this neighborhood to itself. Right? And since we have a minimal homeomorphism, this first return time, it is well defined and it is a continuous function. So we'll have so the whole space will be partitioned into finitely many towers. And then it's just technical scheme that we can consider pick smaller and smaller neighborhoods which converge to this point and make the nested sequence of Kakutani-Rohlin partitions, and we obtain the Bratteli diagram. And then this result was generalized for the case of aperiodic homeomorphisms, and basically one can build some diagram for arbitrary homeomorphism of a Cantor space. And we will be interested in the generalization of this result. So in 2006, Bezuglyi, and Kwiatkowski proved that arbitrary aperiodic Borel automorphism of a standard Borel space is Borel isomorphic to a Vershik map, generalized Vershik map acting on a path space of a generalized Bratteli diagram. So similar result, but for Borel automorphisms. So standard Borel space, the one which is associated with a Polish space, standard Borel space is Borel isomorphic to a generalized Vershik map acting on path space of a generalized Bratteli diagram.
So again, let me ask, because
Bezuglyi, Kwiatkowski. The second name? Bezuglyi, Kwiatkowski. I think he's in Australia now.
So in your definition of a generalized Bratteli diagram, you require that all these vertex sets at every level, they're infinite, right?
Yeah, for generalized, the heights are finite.
Sure.
But
you don't want to include the case of kind of finite.
I mean, no, so it's maybe a question of terminology, so no, here we don't.
So in particular, that means that, of course, I imagine, because you see, you can have realizations like this using finite diagrams, and what you say, you can always do it using these infinite diagrams.
So here it's Borel dynamics, right? So
Sure.
so there it was topologically conjugate, and here it's just Borel isomorphic. So here we proved that we can pick this diagram without minimal and maximal infinite paths, and they use the Venetian marker lemma to build these towers. Yeah, so here they use, so basically they model every Borel automorphism as a homeomorphism of a Polish space, because here they can build this diagram without a minimal and maximal path. So this basis of towers, they have empty intersection.
And we also obtain this condition that at any vertex there are finitely many paths which
Yes.
ends with. Okay.
I think they're using some Venetian Markey lemma in the I think it's in the book of Nakami. I have to look it up. And so they use the results known about Borel automorphism. That it's possible to have this finitely many.
I see.
Yeah, but I definitely have to look it up also. But for sure, yeah, they have only finitely many. It's possible to do this finitely many heights, levels of time.
And Hermann, what is his first name? Is that the same Hermann or a different Hermann?
Richard, I think.
I think yes, I think Richard.
Richard.
Yes. So no,
Not Michel.
no, I think not.
I was surprised that he was so broad. He was, of course, I know, but not that broad.
Yes, and so Bratteli diagrams are used for classification in control dynamics for there are criterions of for orbit equivalence, for Kapitani equivalence, for counter minimal systems in terms of Bratteli diagrams. And we will use these Bratteli diagrams mostly to study invariant measures. So, to study invariant measures, what will be important for us is the Taylor equivalence relation. So let us introduce a Taylor equivalence relation. So it is the definition is the same for standard and for generalized diagrams. So for any two infinite paths in XP, we say that they are tail equivalent even only if they coincide starting from some level. So the tails are the same. So there exists some M such that then this R is a countable Borel equivalence relation. And moreover, it is so-called hyperfinite. So hyperfinite, it means that it can be represented as increasing union of equivalence relations with finite equivalence classes. So R is hyperfinite. So what is Rn? We can just fix n and consider all paths which coincide starting from level n. Then we will also have equivalence relation that's denoted by Rn. It will have only each class will be finite because we have only finitely many levels of each tower, finitely many paths which join given vertex with this equal, and our equivalence relation can be written as the union of R. And let's also see that the Vershik map, it will map, it preserves the tails of the maps unless we have a maximal path. So maximal path can be moved to minimal, which might not have the same tail, but if we are not in the, if the path is not maximal, then it maps to a path which is tail equivalent. And there is a notion of an invariant measure with respect to tail equivalence relation, and in general measure invariant with respect to equivalence relation, but here it's enough to define as follows. So we consider always Borel non-atomic positive measures, and the measure mu is tail invariant if and only if for any two cylinder sets which end at the same vertex, their measures are the same. So for any two paths E0, EE and E prime, invariant with respect to Taylor equivalence relation. Correct? For instance, if we have no minimal and no maximal infinite parts, so like in this realization, then the orbits of the Vershik map are exactly the same as the orbits of the Taylor equivalence relation. So they have exactly the same sets of invariant measures. And this is resolved by Dougherty, Jackson, and Kwiatkowski. Which says that we can that two hyperfinite countable Borel equivalence relation which are non-smooth, in other words, it means they're non-trivial. They are Borel isomorphic if and only if they have the same number of ergodic invariant probability measures. So if we have two hyper non-smooth non-smooth means that there is no Borel set which intersects at the orbit exactly one time. So two non-smooth hyperfinite countable Borel equivalence relations are isomorphic if and only if they have the same number of ergodic invariant probability measures. And another result, it says that every hyperfinite countable Borel equivalence relation is actually generated by a single Borel automorphism. So let's see what it gives us. So we know that if we have a hyperfinite countable Borel equivalence relation, it's generated by automorphism. Automorphism can be realized on a Bratteli diagram, and so such that the orbits of this Vershik map will be exactly the orbits of the Taylor equivalence relation. So basically, combining these two results will give us the fact that every hyperfinite countable Borel equivalence relation is isomorphic to Taylor equivalence relation on a generalized Bratteli diagram. And so if we study probability ergodic invariant measures for Taylor equivalence relations, we are actually classifying hyperfinite countable Borel equivalence relation with respect to isomorphism. Hyperfinite, it means that it is can be written as countable union of increasing equivalence relations which have finite orbits. So it's just also one of the motivations why it's important to study probability ergodic invariant measures for generalized Bratteli diagrams, because it will help us to classify equivalence relations. Or so if two equivalence relations, if they are isomorphic, it means that the corresponding Borel automorphisms whose orbit generate these equivalence relations, they are orbit equivalent. So we can say that we classify equivalence relations up to isomorphic, or we classify corresponding Borel automorphisms up to orbit equivalence. And now let's see how Bratteli diagrams help us to study invariant measures. So assume that we have an invariant measure on a Bratteli diagram. So for arbitrary two cylinder sets which enter the same vertex, their measures are the same. So for every vertex W on level n, we can denote by PWN the measure of arbitrary cylinder set which ends at this vertex. And now let us see, we have incidence matrix. It has historically, we first look at the level below and then on the level above. And this matrix tells us how many edges are drawn between pairs of vertices. So it consists of the elements F, B, W, M. B belongs to Vn plus 1, W to Vn. And this is the number of edges between B and W. And then we can write the following. So maybe let me draw some example. If we have standard diagram, for instance, like this, then the matrix which corresponds to this level, maybe let us draw one more. So we look at the vertex below, we have two edges, 1, and then we have 1, 1, 1. So this will be Fn. And for generalized diagrams, we have infinite matrices. And so, if we want to study invariant measures, they should be well defined, there should be consistency. So, we can write that for every W in Vn and for every n, P and W is the sum of F, B, W, n, PV, n plus 1, over all V and n plus 1. So, if we denote by Pn the vector with the coordinates P and W, we can write that Pn is equal to Fn transpose times Pn plus 1 for every n, where Pn is the vector of measures of cylinder sets on level n. So once we have a measure, we have the sequence of its values on cylinder sets, and vice versa. If we have the sequence of non-negative vectors such that for every n we have this equality, then we can build using this vectors characteristic construction, we build a non-invariant measure. So looking for these measures is the same as looking for sequence of vectors such that for every n they are connected as follows, and all the information about the measures is encoded in these incidence matrices. So now maybe let us pass to the topic of the talk, the horizontally stationary diagrams. So what is horizontally stationary generalized Bratteli diagram? This is a new type of diagrams. They don't appear in the case of standard Bratteli diagrams. So we say that a generalized Bratteli diagram is horizontally stationary. Let's abbreviate like this. If and only if, first, we enumerate vertices on each level with integers. So for every n, let's say we identify the n with z. And secondly, for every n and every ij in z, we want the element ij of the nth incidence matrix be the same as the element I plus y, j plus y. So it means that if we do a horizontal shift, our diagram is unchanged. So for instance, we can have here ij. If we have, for instance, here a couple of edges, then we will have it everywhere. Right? So there is a notion of a standard notion of a stationary Bratteli diagram. It means that the incidence matrices are the same. So usually stationary diagrams are vertically stationary. But here this is a new notion. Why is this new? So why it doesn't make sense for standard Bratteli diagrams? Because if we have just finite, if we have, for instance, a pair of vertices and we have non-vertical edge, then we should translated infinitely many, to the left and to the right. So if we want a standard Bratteli diagram to be horizontally stationary, it should be just this joint union of odometers, right? Otherwise it's impossible. And
Sorry?
yes.
But in principle, I guess you could just fix number k of edges and enumerate vertices of every level by z mod is kz, so and use this formula modulo k, right?
Periodic.
Yes, right in periodic manner.
So it will be like different definition, right?
Well, it's the same, just we identify the set of vertices not with z, but
so you
with
want to
z mod kz.
so kind of close, right? This.
Yes.
I mean, yeah, possibly, but yes, it was a very interesting idea for the research. But I think if we just keep this definition, it works for horizontal especially.
Right.
But you're correct. Yeah, of course, that would be very interesting. And we haven't really used this formula, but just a remark that for horizontal stationary diagrams, we can rewrite this formula in terms of Fourier transforms. Discrete Fourier transforms, maybe it will be hopefully useful at some time. So before doing this, maybe let's consider some properties of these horizontally stationary diagrams. So basically diagrams are very complicated combinatorial objects, and it's always very difficult. So to know measures, we have to know the heights of the towers. And it is the question of the number of paths between vertices in a graph, and it's in general really complicated to compute this number of paths. But for some classes, it is possible, and also these classes usually have dynamical interpretation. Like vertically stationary diagrams, they model substitution dynamical systems. So it usually goes also in pair with some dynamical movement. And so let's look at the properties. So clearly, for also for every level n, for every line AJ in Z, we have of course f a plus k j plus k is equal to f ij. So the number, so for every vertex, of course, the number of, if we fix level n, the number of incoming edges is the same, right? So for every I in, let's say, in Bn plus 1, and for maybe for every I and I prime, correct? So the number of incoming edges should be the same. And this allows us to compute the heights. So let's denote it by Rn. So we have vertices on level n plus 1, and each vertices has Rn incoming edges. Then, for instance, we can compute the height for every vertex on a given level, and the height is just the product of these numbers. Correct? And for standard Bratteli diagrams, actually it's known that Toeplitz subshifts can be modeled on Bratteli diagrams with equal row sum property. Because this equal path number property, so here all towers have the same heights. And moreover, since our diagram is horizontally stationary, also each vertex has this, if we fix level n, each vertex has the same number of outgoing edges, and it should be the same as this Rn. So also for every jj prime in Bn, and it's also equal to Rn. And in general, if you look at incidence matrix, each element, each entry depends only on difference between these indices I and j. So we can say that for everything, Fnij is the function, let's say, of j minus I. So our incidence matrices are so-called Toeplitz matrices. They have constant diagonals. So we can write it as follows. We can, for instance, and it's also a banded matrix. It means that all non-zero entries can appear only in a band around the main diagonal, since we have only finite remaining combinations. So we can write here 0, then first, let's say non-zero element, then last non-zero element, and then again zeros. And then we repeat this row above, shifting. Right, so we can actually associate to our matrix F just this row. And then let's see how we can rewrite this equation. So let us also notice that here dkn, let's say f and ij is equal to b and j minus I, right? In this notation. So we can consider vectors Pn, and they have only finite remaining non-zero entries. And let us look here. So we know that this sum can be rewritten as f as maybe w minus vn, pv, n plus 1. And this will be a convolution of these two vectors. So it will be Vn convolution with p n plus 1. And then if you look for probability invariant measures, these all Pn, they belong to L1. So they have the sum of coordinates is finite. So we can consider also these Fourier transforms for B and for P. So B is just as finite remaining coordinates, non-zero. So for instance, Bn of T is the sum over all integers k, b and k times e. I is complex number, I k t, such that t belongs to this interval, and we can define it also for p. So we get that transform of Pn is equal to transform of this convolution, and then there is this error which says that this is equal to the product of transforms. So we haven't yet used it, but hopefully, so this works for this horizontal stationary diagrams. This is another way to rewrite this information about so if we find the sequence of non-negative vectors which are connected for every n like this, we also get a measure. And I think now we go to the different ways of obtaining invariant measures. Yeah. So in general, there are, like this, we know a few ways of obtaining these sequences of vectors. So in case when diagram is vertically stationary, if incidence matrices are the same, we can use Perron-Frobenius theory to find this. P0 will be an eigenvector, and then each next P1, P2, P3 we obtain by dividing this eigenvector by Perron eigenvalue. And we get this needed sequences of vectors. We can also use extension from subdiagram. And we can use an inverse limit method. So let us talk a little bit about extensions from subdiagrams. So let us do it on the example of horizontal stationary diagrams. So we have such sequence of incidence matrices, and let's consider extension from odometers. So on each level n, we pick a vertex in, and let's denote by I this sequence of vertices, such that each in and in plus 1 is connected by in the case when this is not just, so we can consider as a part space of the subdiagram which corresponds to this IM. So we forget about the big diagram, we just pick the vertices and edges that connect them, and they form also a path space. So we will be interested in the case when it is uncountable. And each odometer has a unique probability ergodic invariant measure, right? Because we want it to be invariant, so we know that the measure of this cylinder is set of this. So if here is, for instance, A0 edges, A1, A2. So the measure of this, each of these cylinder sets is 1 over A0. Each of cylinder sets of length 2 is 1 over A0, A1, and so on. So it's a Bernoulli measure. And let's see when, for such a Bratteli diagram, our ergodic invariant measure is an extension of a measure from a odometer. So there is also a procedure of the measure extensions from a subdiagram. So for instance, this is if we have, for instance, a standard Bratteli diagram which is stationary, which looks like this, we can always put a measure on this odometer. So it will have values 1 over 3, here 1 over 9, and then we can extend to the path space, to the set of all paths which eventually pass through this odometer. So if we denote if our big bar is a Bratteli subdiagram, so it's a Bratteli diagram itself where we pick just some vertices on each level and all edges that join these vertices. Then we can have xb bar is the path space of b bar, and then we can consider a saturation of this set with respect to tail equivalence relation. So it's the set of all paths in the big diagram such that they are tail equivalent to some path from xb. And so there exists y in xb such that x is tail equivalent to b. And it's possible to extend our measure with an equivalence relation to invariant measure on this, its tail invariant subset. xb bar is tail invariant because it consists of paths which are tail invariant to our path space of subdiagram. And if we want to get invariant measure, we need the measure of this cylinder set also to be 1 over 3. Then the measure of each of these cylinder sets 1 over 9, and so on. So we can define our measure on this space, and now if we say that the measure of all other paths is 0, we define it as to be 0, then every ergodic invariant measure on subdiagram extends to ergodic invariant measure on the big diagram.
But not necessarily finite, right?
So it can be finite or infinite depending on the number of edges. So for instance, it was proved in 2010 by Bezuglyi, Kwiatkowski, Medinets, and Soloniak. Bezuglyi, Kwiatkowski, Medinets, Soloniak for standard Bratteli diagrams, which are vertically stationary. We can always rewrite, like renumber the vertices so that we have our incidence matrices have so-called Peron-Frobenius form, or Peron-Frobenius normal form, so that we have these blocks in the incidence matrices which correspond to vertical subdiagrams. And then if we have, maybe if we look at incidence matrix, it should be like this. So if we can put measure on each of these subdiagrams, they would be simple and they would be, if it's stationary diagram, then they're uniquely ergodic. And then each of these measure we can try to extend on big diagram. And if the Peron, so here it can be not a odometer, it can be some finite matrix. So if the Peron-Frobenius, the Peron eigenvalue of this matrix is strictly smaller than Peron eigenvalue which corresponds, of the matrix which corresponds to this subdiagram, then we have finite measure extension. Otherwise, if it's greater or equal, we infinite measure extension. So for instance, here we can compute, right, we can compute the measure of this cylinder set. So let's denote by M, so M bar is the measure of subdiagram. Let's denote with bars symbols that belong to subdiagram. And the height is extension. So the measure of this, let's denote it by E, maybe I don't know, E0. It's equal to 1/3, right? That divides into the cylinders plus 2/9 plus 2 squared over 3 cubed and so on. Correct? So here we will have finite sum, but of course if we put here already 3 edges, we have infinite sum. And this works in general for more complicated cases when we don't have just odometers, but arbitrary, but some subdiagrams with a simple, with primitive incidence matrices. Okay? So it's not anymore true in case of generalized diagrams. This result doesn't hold because we can have here infinitely many components, and we proved it with Bezuglyi and Kwiatkowski. So we need more strict conditions for finiteness of measure extension. This is not enough anymore. That we have just this eigenvalue is smaller than this one, and that is trying to apply this result for horizontally stationary diagrams in case we have some odometer. So we have our vertices I on each level n, and there are corresponding elements of incident.
So what is that formula over there?
Which one? This one?
Yes, it looks very interesting.
It's how we compute the measure of the set of all, the measure extension for the set of all paths which start at this vertex. So this method of, this is one of the ways to obtain ergodic invariant measures on the whole diagram. Sometimes they sit on subdiagrams. So here the structure of a Bratteli diagram also helps us to determine the measures. And so here let us consider the example when we have two vertices on each level and the matrix and the diagram is vertically stationary. So we draw in the same way. And here we have two components. This is a minimal component for Vershik map or for tail equivalence relation. There is always a measure 1/2, 1/2, but it is not a full measure. It doesn't extend anywhere. There are no edges that go to this component. And we can also put a measure here, so it will be Bernoulli 1/3 measure. And then we want to extend it. We have edges that go this way to extend it on the whole diagram. And we want to use the fact that our measure has to be tail invariant. So we have this edge. It corresponds to cylinder set. Its measure should be the same as the measure of this cylinder set. So it should be 1/3. Then the measure of each of these two cylinder sets should be the same as the measure of each of these, so 1/9. And so on. And the paths which are just always in this component, they should have this extended measure 0. So the measure of the set of all paths which start here can be computed as this. We have this disjoint cylinder sets of non-zero measures.
What is in the numerators?
3. So powers of 3 because we have here.
These are denominators, numerators.
No, 2. Powers of 2 because we have here 2 edges, then we have 4 edges. And it is a baby example, but the same happens in general. It's just more complicated. So here, if we have some primitive matrices, incidence matrices for each component, it is known that their elements in the power of these matrices, they grow as powers of Perron eigenvalues. And so we can also say when this sum will be finite or infinite for standard, for usual Bratteli diagrams. And for generalized diagrams, we can have here infinitely many components. And then it's more complicated. It's not enough to say that just this eigenvalue is smaller than this. We need more conditions to get the finite measure extension. And we have the following result for horizontally stationary diagrams. So if we pick vertex IN on each level n, then we will have our Bratteli subdiagram will be a odometer which has this number of edges between consecutive pairs of vertices, right? It's just the element of incidence matrix which corresponds exactly to In plus 1 and In. So we can always consider the measure mu on this odometer, the unique ergodic invariant probability measure on our odometer V bar. And let us denote by sigma n the sum of the entries of the incidence matrix. So we have here a vertex In plus 1, so it depends also on our choice of i's. I think so. Yes. So let us denote by this sigma the sum of the number of edges which go outside of odometer, which are not inside. So here is inside the odometer, and here is the sum of edges outside. So we can say that the measure expansion to this, let's say, to this set of paths which are tail invariant to the paths from odometer is finite, if and only if the sum over n greater or equal to 0, sigma n I over f In plus 1 In is finite. So this actually, this is not difficult to prove. It follows from this from similar considerations. So I don't know if there. Maybe I will just write the formula from which it follows. Or maybe even maybe later if we have time. I don't know. Maybe I'll just yes.
So in particular you need that this number Fin plus 1 In that converges to infinity.
Yes. So let's look at example. If we have a following class of horizontally stationary diagrams, I don't know, let's call it smaller. So it's not necessarily, it's not vertically stationary. If we have the following diagrams, so the incidence matrix on level n is as follows. It is Am for I equal to j, 1 if we are above or below diagonal, and 0 otherwise. Then there is the pressure which is extended from each of those odometers, if and only if, and which is this finite measure extension, if and only if this series is convergent. Because here edges that go outside, there are just two of them, so there will be, if we use that theorem, we will get the following series. Right, so if we have this, then they write this countably many ergodic invariant probability measures on the whole diagram which are obtained as extensions from these odometers. Let's denote them maybe by UI. So here we have just vertical odometers, so corresponding to 0, sequence 1, sequence. But the question is, are these all ergodic invariant measures? So before we had considered a situation when we don't have the edges that go in other directions. So before we considered the following in previous papers, the Bratteli diagrams which are whose vertices are generated by natural numbers, and we just have extension in one direction. So it's similar to this situation. And there the whole path space was partitioned into sets of paths which are tail equivalent to the paths from some of the odometers. So it was a partition into invariant subsets, and it was clear that these are all possible methods. But now we have more complicated situation. So who knows? Probably there is we can go along this odometer, then for longer time along this odometer, for longer time there, and maybe there method which can tell us how many there are ergodic invariant measures. So for such diagram, we proved that so if we have this condition, then all ergodic measures are of this form.
So when you say this condition, it's not a condition on the diagram, right? It's condition on
Formulate.
Oh, because it's stationary. I see. Okay.
So it's horizontally stationary.
Right.
It's not vertically stationary, of course. So theorem, if our Bratteli diagram is generated by this incidence matrices over there, and this series is convergent, then all ergodic invariant probability measures coincide after normalization with those extensions from odometers. Coincide.
So just to check, so if we have infinitely many copies of Pascal diagrams, then we have an equal to 1 for each n, so this condition is still not satisfied.
Yes.
It's not counted.
Yes.
Then we have continuum.
Yes, we have fitted. Yes, we have joint paper with Artem and Sergei Bezuglyi about other Bratteli diagrams which contain infinitely many Pascal Bratteli diagrams, and there are uncountably many measures. So maybe the next time. So let me just explain this inverse limit method. It was first studied for standard Bratteli diagrams and then for generalized. So remember that to find a measure, a Weyhead measure, we need to find the sequence of vectors Pn such that Fn transpose Pn plus 1 equals to Pn. So it's just a technical thing to simplify formulas. Instead of Pn, we consider, so instead of sequence of values of measured cylinder sets of level n, we consider sequence of values of measure on towers. So remember that xwn, it was the tower which corresponds to vertex w on level n. So it was the set of all infinite paths that pass through w on level n. So the measure of the tower is the measure of cylinder set times the height. So if we have a Bratteli diagram, with then it's fixed, then also measures of towers will give us measures of cylinder sets, and we have to measure which is completely defined. So that's where the heights are hidden. So it's sum over W. No, yeah, it's fine. It's not sum. It's space. So measure of the tower is measure of cylinder set times the number of cylinder sets. And then if you look for probability measures, then the sum over W of measures of towers should be 1. So we have, this gives us a normalization of this vector of cylinder sets, because otherwise it's shrinking, it's getting smaller and smaller. And for us it will be convenient to work with the normalization, so with like some sort, maybe in some way normalization. So let's denote by Q and W the measure of the tower. And we have vector Qn, and now these vectors Qn are joined with each other using stochastic incidence matrix. So we can introduce F tilde n is stochastic incidence matrix, which is defined as follows. F tilde VWN is equal to F VWN times the height of the tower W over the height of the tower V. The structure of the diagram provides us with the formula for the vector of heights. So it just follows from the fact that each height on level n plus 1 times the corresponding entry of incidence matrix of levels n. So we have this formula, and it implies that this matrix F tilde is stochastic. So sum over W F V W tilde n is 1. And we have the connection for every n, F n tilde transpose Qn plus 1 equals Qn. So here Q is a stochastic vector. It's the vector which corresponds to the measure of towers. And this is stochastic incidence matrix. So basically it's the same, but we now always work with stochastic vectors. And let us fix some arbitrary natural number n. So we can say that the vector of the values of tower of the values of the measure of towers on level n is equal to our stochastic matrix transpose times Qn plus 1. It's equal to Qn plus 2, and so on. So we know that for sure for every n, Qn belongs to this delta n. Delta 1n is so n here just to indicate the level. That is, we are working we want to find measures of Bratteli diagrams. So on the level n, we know the vector of measures of towers belongs to this delta 1. So it's delta 1 does not depend on n, but it's just to show that it's measures on level n. So it's all vectors with infinite coordinates. Maybe let us use some other notation. And now we know that it's not just this, it comes from Fn tilde, so it also belongs to Fnc. Correct? It also goes from it also goes from here. So let us denote in general by delta 1 and m the image of we have Fn transpose tilde and so on until n plus m minus 1 transpose of delta n plus m 1. And our Qn should actually belong to the intersection when m from 1 to infinity of delta 1 and m. Now, in case of standard Bratteli diagrams, these are compact sets. We always have non-trivial intersection. In case of generalized, it's not true anymore, and we want to use some Crane-Needman types of theorems. So we have to take the closure of this delta 1. If we take the coordinate, the topology of coordinate-wise convergence, then the closure of this delta 1 is the set of all sub-probability vectors. For instance, 0 vector will be the limit of basic vectors. So this theory also it appears in the theory of countable Markov shifts, where people work with infinite matrices, and usually they use different dynamics, but they still have some results we use for infinite matrices. So we consider delta is the set of all sub-probability vectors. And then we will have non-trivial intersections, and ergodic invariant measures will correspond to the extreme points in this inverse limit. And in case when we have, what does it mean that we have no measure? In case when this intersection is just 0 vector. So if we have just 0, 0 vector, it will, so now since we did this compactification and closure, we have compact sets, we always get something here, but we can have just all zeros. And we showed also in one of our previous preprints that this vector Qn of these measures of towers can be obtained as the limit when m goes to infinity of, I need another notation, so let's denote by G tilde and m the product of these matrices. So it will be f n plus m minus 1. So call of G, I, M. So let's say if we fix G, G, I, M, J, and M. So basically we have like extreme points in this simplex, and we have transpose like basic vectors, right? And then we have transpose matrix. So now the image of this basis vector will be not column but row, and then extreme points should be the images of extreme point. Like we use like Crane minimum theorem to say that how the extreme points should look like. If we have something like this, it doesn't guarantee that we have an extreme point, but it is like necessary.
Excuse me.
Yes.
So when you write I think T here, doesn't it? So for instance, there Qn equal to intersection of delta 1 and m. Do you claim that intersection is a unique vector, or?
It can be even sorry, if we don't compactify it, it can have empty intersection. It can have a few. Huh?
Do you have more? Is the intersection just one point, or?
Not necessarily. No, I mean it depends.
But
on
here
the
you
matrix.
write limit.
And then you write equal. So you mean?
Here we can pick different IM. So basically in those, we have bigger and bigger here products, and we pick some rows, and we can change. So for instance, for that example where we have vertical odometers, we show that there is a limit if we fix this I, and then we have countably many measures which correspond to each I, and we just prove that the measure which is obtained like this is equivalent to the measure which is obtained as extension. So for instance, we have a formula for a cylinder set. If we have this measure extension from I to vertical odometer, so then the measure of a cylinder set which ends at vertex J on level n, it is the number of all paths between I and J. So here's the limit as m goes to infinity. Here I belongs to Vn plus m, J belongs to Vn, and here we divide by the product from A0 to An plus m minus 1. So basically we also in our formulas we have this horizontal stationary diagram, so we can write a big formula for the number of paths between I and J, and we can do here computations, and we can compute Radon-Nikodym derivative. So for this measure which is extended from isodometer and measure which is obtained as this inverse limit method. And we can compute measures of cylinders and see that they are always the ratio for every cylinder set, the ratio of the measure of cylinder set which is obtained where the measure is extension from a odometer, or when the measure obtained from the inverse limit method, let's denote it by mu y, of this again the same cylinder. This ratio, we got that it was the product of An plus 2 over An, where n goes from 0 to infinity. And remember, we assumed that this series converges, so this product will also be just a number. And this, and we show that the measure that we obtained from inverse limit is equivalent to this measure. And these measures, we know they are all ergodic. They all have, they are supported on these joint sets. So this will be also ergodic, and this will be all possible measures. So I mean, of course, it's very. I understand that it's just an idea, but basically we have like 3 methods to find ergodic measures. For vertically stationary diagrams, we can look for eigenvector. For general diagrams, we can look at the extension from subdiagram, but it does not guarantee, tell us exactly how many measures we have. On the inverse limit method, it's the most general, the most difficult to apply in particular cases, but basically we look at the extreme points in this inverse limit. So maybe this is our main results, and also we have results about Vershik map on horizontally stationary diagrams. We have criterions when this Vershik map can be prolonged to a homeomorphism of the path space, in case when we have also horizontally stationary order. So we just order the incoming edges in the same way for vertices of a given level. Then we have countably many minimal and maximal infinite paths which are all parallel, and we give conditions Vershik map. It always can be prolonged to Borel automorphism, but it's also interesting to have continuous models sometimes. So we see when it's homeomorphism. And we also consider Markov measures on Bratteli diagrams, so we can put weights on edges, and the measure of a cylinder set will be the product of the measures of edges. And we give condition when such measure on horizontally stationary diagram will be tail invariant also. So maybe I can finish here, so thank you so much for your attention.
Yeah, I have some questions. So first in this formula for product of an plus 2 over an, so if your series of 1 over n is finite, then
Yes.
an converges to infinity.
Yes. I
So
think we used some result that the product is finite if and only if here will be so we rewrite it as 1 plus 2 over an, and then there is a result which connects convergence of products and series.
I saw the plus 2 is in the
Sorry, no,
index.
yes.
I misread it.
Yeah.
Okay. Any questions? So I still didn't understand from the formula in the corner down on the left, qn equal.
Oh, below, sorry, of course not over, and now I understand it for no,
Okay.
belongs. I'm
Okay.
so very sorry, it's not equal, it belongs. Because we can have many measures, we can have uncountably many. It should just belong here. So for instance, if we prove that this intersection consists of only 0 vector, then there is no measure. I'm very sorry, yeah, it's
No.
yeah.
I have a question. But it's a philosophical question. So my impression is that you are able to construct lots of invariant measures. So you produce dynamical systems in the sense of ergodic theory.
Yes, so if I may, for instance, I think, so I was talking to Bratteli-Vershik, and he noticed that in some of our papers we could construct on a Bratteli diagram a Vershik map which on a minimal homeomorphism of a Cantor space which has 0 entropy and countably many probability ergodic invariant measures in that countably
That was
many.
exactly my question.
and
Whether this can be used to produce some counterexamples in ergodic theory.
Yes, exactly. So they are very good to build, to construct some examples with prescribed properties.
So maybe I have a question in the opposite direction. So are there any kind of reasonably simple diagrams, say generalized, when you don't know whether there is a unique
Very many. So
invariant
unfortunately,
So what would be the simplest? That's the
yes,
first one.
thank you for your question. So for instance, if we have a Bratteli diagram which has on the, so when we don't know, right, which has the following incidence matrix. So here we have vertical odometers which grow, and here we have single edges. So we know it's vertically stationary. So it's the same matrix, and we know that there is no finite Kironic invariant. So if there is, so we have a hypothesis that there are no probability ergodic invariant measures here, but we are not able to prove it. Because if there is, it should come not from eigenvector and eigenvalue. And what we know, if we erase things like this, or wait, I was confused which one is. So if we consider, for instance, a diagram which is like this, so yeah, it should be, I think, the following instance matrix, then there is no probability ergodic invariant measure, because whenever, if we assume it exists, it should have, at least for some of these cylinders, some of these sets on 0 level, it should have non-zero measure, and then the extension will get us already infinite measure, so here. But if we put here more ones, it becomes combinatorially much more difficult, and we assume that there is no measure, but we still are able to prove it, and it looks really simple. Also, we have equation, so once we have an eigenvector, it gives us a measure of these sets, right, which starts, of these cylinder sets, which start at these points of 0 level. And it's important for us if the Kironic eigenvector has the sum of coordinates which is finite or infinite, because it gives us either finite measure on the whole space or infinite sigma finite. And we also don't know of some easy verifiable conditions on the matrix to say whether this sum of coordinates finite
maybe online participants. So, Sasha, Dominika, Daniel Pavlovich, Tomasz Gimecek. Okay, let's
Yeah, thank you so
send
much.
again.